G'day mates, this is Hamaki Yingli, and I hope you had a really wonderful Juneteenth of 2025. And as promised, according to the Discord chat, I'll be having another live stream to finish up Ring 2, namely the challenge Electrons. We had a lot of time and enjoyment examining the remaining Clifford gates, the combinations of the poly gates, the H and the S, the exploration of the basis states, and implementing classical computation using quantum gates. We will follow this up by live streaming each and every of the challenge electrons in this live stream. So remember that I will be announcing the future live stream sessions, namely that of Ring 3, sometime later today, but please remember I will likely be busy joining several intensive networking events, as well as working on both of my startups and the Global Industry Challenge. And unfortunately, next Unicom might be delayed a bit. Let's start our live stream right now, so this is our Zoom. So let's go to descent mode. So this is our current state of the map right now. So we discovered a new type of electron called the phenomenon electron, which has applications on basic quantum algorithms. These are the algorithms that are specifically quantum. That means they are implemented in such a way that it is asymptotically better than the best known classical algorithm. So it's not easy to make a quantum algorithm. It's a double whammy to design a quantum algorithm. The difficulty is twofold. First, you have to design an algorithm, and secondly, it has to be better than any known classical algorithms. And then, the implementation of quantum computers is still in its infancy. So we will see ideas of phase kickback in the Ring 3 live stream. So that's the Sage of Reasons, which we knew since we went to the measurement transform. Okay, we will start with the nodes on the main path, so we will do the Clifford challenge. Okay, this one is nothing more than Y and S, but here it actually also they also supply you variants of the basic polygates, so the answer for that will be neg Y. Okay, this one appears to be a negative of SX gate, so H neg S H. Let's see this. Okay, H neg S, so let's try flipping this with a Y as well. So it's a 4-gate solution. This one looks like, okay, so you have to perform neg x Okay. HH, then neg X to turn them all red. Okay. This thing looks like a swap, so swap gate, but I don't think you really even need a swap, so here, apply a negative Y to send the face backwards, and then an X. So you don't need a swap for that. This one is easy, so however you're not supplied with an SX, so you can try to make a control, so there's a shortcut for that. So you get like a brilliant solution 1 gate, but that's not how the solution is intended. So I'm already in bracket 10. Let's try again. Let's try the SX challenge. This is a crucial tool in quantum computing because it allows you to form yin-yangs instantly, as well as join the yin-yangs. So let's try a double SX. So double SX, interestingly, does not cancels out the yin-yangs. Let's go with combinations of... Okay, this one appears that you may need this one, it appears that you may need a controlled operator, but there is no controlled operator, so you have to use... I think the best way is to use a Z. So it's going to be H and SX, followed by a Z on the first. We saw that has the effect of cancelling out the colors. Okay, so now it's color cancellations. Let's try S and H. So here's the thing. Now we can perform X on the outset and then an H. Okay, so there is a 0 gate solution, so that's a glitch. And this one is straightforward, so it's SX, then you apply Z, you apply an H on the other two. Okay, so we have SX, then we have this thing is actually an X. So we join let's try joining the SX back to see if the colors are preserved. But it does not supply with you an X, so let's see if an HSH is also a possibility. Okay, so you have a yin-yang state. So just I without the green. Okay. Just negatives. Then we could generate greens by taking out by doubling down the Sx. So H So here's the answer. It's a little bit rough, but geez, I have the most number of gates. The actual answer has just 2 gates. This one should be easy, so just negatives. So we could perform Y. Then we could perform an Sx. Then we could add an Y on the middle. I think it's better to add an X because this term is more advanced than the last. Okay, and it does not provide you with an Sx, so this is the opposite, so we have to do a 0, 1, 0. Then, if the 1 is also there, we can advance. So that's my solution. So the best answer still has like 4 gates. So there it needs to have a 2-gate solution for the just I without green. So can you do that? So there's definitely a flip. Then I have to try and error that. Okay, we now have Sx and Z and Sx. So what is the effect? We know that this is a Z, but that's an X, so these two are switched. But Sx, Z, Sx has the effect of implementing a... I feel like this looks like root Y or something, but I kind of forgot. So just negatives, so that means just the negative yin-yangs. So we will try using I, then we perform an Sx in parallel. Okay, this one needs more advancement than that. So let's add a S and then add another S. This is the 4-gate solution in depth 2. Bracket 6. Now we will deal with learn the final gate called the T gate. This is an especially crucial component, even though it looks like a generalization of the S gate, because it's the first gate that breaks Clifford. The subtle twist is it is essential for building more complex quantum circuits. That means, let's see like the sequence HT powers of HT over and over again. It creates intricate quantum states and enhances computational capabilities. We need this HT sequence, HT powers. Okay, this is nothing more than XTX, so it's an XPX gate. We don't even need that either. But there's a 2-gate solution over there, so we could do an SX, and then we can add a T to negate the yin-yang. Okay, this is the T-gate in respect to the X basis. So we can, so this thing can be thought of as a quarter of an X. We add another SX and then a quarter of an X. Okay, so a quarter of an X. I think it's best to just add another X. So 5 gates. Okay. This one appears that you may need to generate a quarter of an X on the first qubit, so HTH. And then you have to apply another H on the other side. Now you have to apply another T gate to perform a flip. So this is definitely something a little bit trickier, but we saw this phenomena. So HT could be used to reflect the alignment of the complex value. Okay, this one should be easy, but here, it provides you with an HTH. So now you have to perform an HT. HTHTH. Okay. You may need this time a Y gate. Y, then HTH. X, then HTH. Then HT. Let's try Y and Z. So it's not easy but doable. So why is there a T over there? So we could use H, T. Okay, here's a trick. We could try to exchange the colors using Y. Then we perform another H. Okay. But now it seems like there's a reflection effect. So we don't want this reflection. Okay. So we could apply a Y. Now we could apply a Z. And then an S. Okay, you can then so here is the new answer. So we now need a control gate. So, but it's doable. So okay, so we need like a sequence of 3 gates now, so let's try an X. We need a Y. Then we need another Y. And a Z. It's a clutch. So I have the bottom over there. So now this thing looks like HHHTTT. Okay. This thing definitely looks like a basis transform. So HTTT, then we could do another T. So S, then Z, so S, H. So sandwich them all. And I got the brilliant solution, but interesting enough that we have an 8-gate solution for that. So can we see like not easy but doable? So not easy but doable. So we'll try SX instead, because it's supplying you with that. Okay, now we see something more friendly. The power of T's. We do this again. Now we have 2 opposite colors. Okay. Then let's apply a Z to cancel out. Now we have these yin yangs. Let's try the T's. Okay. We now have a roadmap in mind, but the thing is being split. We merge this with H. Let's try an SX. Okay, this looks a bit more friendly now. So this thing can be reduced to an S. Now we can apply an X. Then we have, I think the Y would be a shortcut. Y. Then we would have controlled Y. So here we need to move the X again. Now we need to perform a... Okay, so there's a double control gate, so double control. Okay, so we have the idea now, so we can now apply a final Z. Okay, we have an X, and then we have a Y, X, so control. I think it's better to do this, so control. So that's my current solution. Now this one's worse. It's 12 gates. So I'm still on bracket 7. Okay. We will move on to the only electron on the short branch, only challenge electron on the short branch. So this one would feature many HCs. This one's easy, this one it's an H on the first, and then there's controlled H. Now we have a yin-yang, so that's nothing more than applying an S. X. So that's a controlled SX equivalently. Okay, there is an unequal superposition, so controlled on the ground qubit, we apply an H. And now on the let's apply an H on the first, so qubit 2, so we can apply an X next. To apply two controlled gates in sequence. Okay, the answer for that would be anti-controlled. So it's an anti-controlled. So it's an, okay. Now, on the right hand side, we can apply an H, so let's go with that. Then let's try an X. Okay. But there's also another thing. So we now have, do the colors match up? The colors, this one will require a swap, so we do not want a swap. So okay, so here we can work with only on the right hand side, so we can perform an S gate, an X gate, so we would have opposite colors, and again another H. Let's try flipping the order to see if this is correct. Okay, because there is only one downwards, one backwards pointing qubit sigil, so this might call for some controlled operators. Controlled. So but we're not given an x, a z in this case, so we have to implement this using x. So break 2 in all colors. Okay, so the first answer, let's try applying an H preliminarily. We will deal with the next later, so we deal with. Now we have a better mix. Okay, now we have the combination we wanted. So, and we can also anti-control that. Okay, so now we have the correct combination. We now need to anti-control the x. So x, anti-control that. Okay, I think we only need, okay, I think that's correct, we don't need another switch. So we have a brilliant solution there. This thing looks like this thing is nothing more than a GHZ problem. So control and then change the x position and another x. So now we finished, we're on bracket 8. Okay, let's move on to Entanglement challenge. So, cosmic connections. There isn't many bracket 10 players out there, but do you think we can get to bracket 10? This is Bell state. 5 plus. Okay, there we have this rather odd looking gate, but that is, could this be like an implementation of 5 plus? Okay, so here we control this x and then we reverse the gate. This is phi negative, so we just add an x over there. So we can do this without using z. But there is a method that uses z, so it's going to be h So there is a 3-gate solution to phi or phi of x. Okay, this one is a negative psi negative, negative psi negative. So we already are provided with Hadamard. Okay, we then perform control x. We add a z. So the z does not have an effect. So we perform another x and a z. Okay, but now we need to switch the colors as well. So how to do that? So ZX XZX. To reduce the depth, but the actual answer has only 4 gates, so I think we could just use a Z to fix this thing up. And then we could use a controlled X. So there's a 6-gate solution. Okay, this is another implementing of a GHZ gate. So GHZ, then we perform X, and X, and X. This is a negative of a GHZ, so now we can switch the Z together, so okay, so this thing looks like we could apply a XHX, so make it into a Z. Okay. So after merging, we could get special entanglement. This one should be easy, but let's say we have that. So okay, the best idea is to try to use a double Z. So double Z to cancel out the Z. Now we can use an H again to unmerge. Now we are left with something we wanted, so we need to entangle this 3 ways. So we need an XX, then we need an H, then we have an H, X, X, X. So the actual answer should have 5 gates. Okay, this one, let's switch to the right hand side. And let's try performing the entanglement in reverse. So 1 1 1 1 0.71, 0.5, okay, 0.71, 0.71, but this is an entanglement state, so 1, so if this is right, okay, now we apply 1110, so we need to anti-control that. So 1, we have controlled gate. Now we can do the H. Then X, so GHZ. Warm flip. So So my gate is rather dirty. So I'm only on bracket 5 this time. We now have the Toffoli challenge called the triple control. So we will be introduced. This is a direct follow-up to the Toffoli gate, so the double control. However, we can use Toffolis to create multi-controlled gates. So this is a... So first you control, then we control XX. So blue-red Toffoli. So we need to perform cross over there. So why is there an X over there? So unsuppressed Toffoli. This one's very easy. It's nothing more than an X, another X. Except you can do this in series. Let's go back. So here we can attempt an H the first round. Then we can attempt an X. And then we have a double X. But now we need to leverage the power of basis transforms. So how to do that? So XHX is equal to Z. Now we have the singlet, still a Toffoli state, so here. Except this time it's inner, so we still apply an H, and then double X. But the H, let's do it this direction. a basis transform. So we can place it on the other side over there. So now there is a yellow. How can we handle the yellow? So the yellow can be done using this. So controlled XHX. Now controlled X. So it's still a Toffoli state. So this is an extremely suboptimal solution I have, but we need only like 4 gates to perform. So the first hint is to use H. Now we control that. So control the X. Now we control the X. So still suboptimal. Let's go back to blue-red Toffoli. So blue-red Toffoli, you're not provided with a Z, so you have to use H's and X's alone. HXH. Okay, now we have the solution. So if the 1 is there, we apply an X. So now we have the solution. Still unsuppressed Toffoli, still a Toffoli state. So it's still a Toffoli state, so there's a hint. Use the same idea as last time. So, except this time, in fact, there is no Toffoli. After all, there's no Toffoli. Turn a Toffoli into 2-qubit entanglement. So, you don't need a control gate for that. This one, you're doing it in parallel, but the idea is the same. All you have to do is this. If the second qubit is 1, then you switch the position. So there is no Toffoli, actually. There's no Toffoli. There isn't much Toffoli in this. So I'm able to get into bracket 9 for that, but this puzzle, to be honest, it's quite flawed. We're now left with the last of the puzzles, Boolean Cascade. This one is relatively tricky because it asks you to have to like reuse qubits. Only attempt if you're familiar with a condensed version of these Boolean operators. So now you are supplied with custom gates. Okay, so here, make it true. So basically you want an XOR on the first and the second. Okay, this one looks like an AND statement. So basically perform an AND. Perform an AND on the... So make it true again. So perform an AND on the second. This is the same idea, so we have drag my masters. Okay. So which one is the bit that acts like an OR or an AND? So this one's definitely a tricky beast to deal with, but so let's say like an AND on the so let's say we could perform an AND on qubit 1 and 2. So basically you only switch if in respect to the last qubit if both of the 1 and 2 are true. So that means okay. So let's try with NAND. NAND is obviously the trickiest beast to deal with. NAND. Let's see. Now we could try an OR. And then we would have to use one of the last remaining. Let's try an AND on 13. Okay, we now seem like we have the solution. So we should try an OR. We could try another OR. So this is a 2-level OR. Basically now we have to like recycle the outputs. I got a brilliant solution this time. Okay. This one we look over like an AND of the first and second. Qubit 2 first and the second. So now we do it on the ground. So AND over there. But now we should try to use a NAND to send the qubit to the other side. So NAND on the second qubit. Let's NAND these two together. Then we perform an So we perform an AND, or an OR. So AND of that. Okay, I think the answer is this. It's a confusing puzzle, so these two literally looks the same. So the only thing I have to say is this puzzle needs some rework. Okay. We have this never a straight line towards the ultimate truth. Okay. We need to... This is a 5-qubit system, so NAND, 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 NAND. This is a seriously inconsistent puzzle, so what to do to switch these two? Okay. We now see something valuable. Perform another NAND to cross to the other side. We don't need to cross because there's already a crossing. So all we need to do is to put it on the right side of the left half. So NAND. We perform another NAND. And then finally another NAND. Okay. So, I think we should use an AND instead to flip the polarity. So switch the last one only if the next two are equal. The only thing I have to say about this puzzle is this puzzle needs some rework. It's confusing, like the two differently permuted versions of the gates are not the same, but they look the same in the circuit editor. So this is definitely something that is not correct. Embrace the square root of x. We will deal with we will revisit some of the modules to find better solutions. You have everything you know, so not easy but doable. Okay, so again, you need this T gate is something of significance. So now you have these two, and then you want to merge them together. So, okay, now we have something easy. So, then how can you flip the... can you flip across, reflect on the... So let's try H SXT SXT XXT. Okay, now we see a solution. That looks good. We apply another SX. Let's try staggering these two. Let's try mixing these two together. Okay. Okay, now we see a nice looking pattern. But can we merge these two together? So there is when you can perform like these bit flips. Okay, do you think this could work? So SXT then SX. But these are of the opposite halves, so you don't want that either. Okay, the best way is we could try to attempt an H and then a Z. Control Z. Over there, then perform an H again. Then Control X. let's try the other one. So give everything you know. So we could express this in terms of s-axis instead. So this is an sx and another sx and another x. So I have to solve this with like 8 gates. I think let's try using just s-axis, might give a shortcut. Okay, so here's the thing. We could just use a T to convert this thing into all opposite colors. So now we then could merge the circuits together to form an H. Okay, now we can also apply another T to make the colors all solid. We could then apply another T to make everything solid. So we now apply an S, a Z on top. So we have this. We can do an SX on the top, SX on the bottom, then we have an S, so we now have a Y, H, okay, here a yin-yang is okay in this case. So yin-yang. Let's see if we can move the yin-yang out. Okay. We can now apply another T gate. Y gate. So I have a 9-gate solution now. So it's the less straightforward solution, but the optimal solution if you want like the less depth, then it's going to be 12. We revisit on the SX gate. We now do a T on the Is that on the right? Okay. Okay, now we have like these in series. So let's see if this is possible. Okay. So now we need a double control, so double control. And then X. So now it's a slightly better gate, but can we do this in 5? So can we flip this in just 5? So let's try skipping this out. We can get this thing out of the way, so HTH. Okay. Now we have an easier solution by just skipping this T gate. We advance the T gate. Okay, now we have a 4-gate solution. 4-gate solution. Gonna be dinky die. Oh yeah! Oh yeah! 4-gate solution for... It's not easy, but it's doable. By just skipping through the entire supplied T-gate. So this is a state of the affairs, but I have to say Boolean Cascade needs some reworking. Okay, so the ring 2 challenges. What we achieved is we achieved a new solution so new solution for a T-gate T-gate number 4. So I have recorded this on the realm, so which is hard but doable. So for hard but doable. So you got this now. Okay. We end this session with We end this session regarding a note on the classical gate challenge. So bug report. So classical. The problem is on the circuit editor, it is ambiguous. The 3-bit classical simulation gate. So it's 3 qubits classical simulation bit is ambiguous. The master slot. The master slot should belong to the output qubit. So I have actually, you can actually see this while I was trial and erroring the puzzle. So we have this. So we have this. Let's try the and. Then we have the other two inputs, M and M. This AND should be an output. M should be an input. M should be an input. But not that the AND gate, so this gate, so AND, should be an input, while the others are, well, one of the M's is an input and an output. So that would not work. You could easily mess this thing up. In other words, this permutation between the two M's are not equivalent, because one of these choices represents the second input and the other is the output. So I have raised this bug, and once this has been fixed, it will be live streamed again. So I unfortunately have to pause the live stream session on the classical simulation path, but we will continue as normally for the quantum phenomenon path. So I hope you enjoyed this video and are waiting for more of these live streams. Like and subscribe to my live streams for Quantum Odyssey and beyond. Hope we can like unlock the universe now as we wait for the other Independence Day on July the 4th. See ya.